Well, hey everyone, Mrs. Hanson once again, ready to wrap up our lessons in thermochemistry with our last video lesson. A little bit of work left to do. Let's take a look at an example of a problem applying Gibbs free energy and solving for actually the temperature at which the reaction becomes spontaneous or not. To calculate temperature at which the spontaneity reaction changes from spontaneous to non-spontaneous or vice versa, we assume the delta G then to become a value of 0, and that's defined as the state of equilibrium. And again, I'm going to emphasize equilibrium is coming to us over and over and over again in the next 3 chapters. But defined equilibrium is saying that the rate of the forward direction is the same as the rate of the reverse direction. And write that with me. That's the equilibrium. If A and B are in dynamic equilibrium with C and D, we have a forward direction and a reverse direction occurring at the same rate. That is the definition of equilibrium, and therefore delta G is assigned 0. And we know that if delta G is equal to delta H minus T delta S from our last lesson, and at equilibrium, 0 is the value of Gibbs free energy, we begin to rearrange this equation, pulling out T, the Kelvin temperature at which a reaction becomes spontaneous. An equation where the Kelvin temperature is related to the enthalpy over entropy, solving for the temperature. So delta H over delta S pulls out T, the temperature. Let's take a peek at an example. And here we have an idea. Let me make this a little bigger. And now I have to pull these down. These are the delta H values. I should have had this just a little bit bigger. There we go. Okay, so now we have an equilibrium temperature for a phase change. Let's read through this together. As defined in the chapter on liquids and solids, the boiling point of a liquid is the temperature at which the liquid and the gaseous phase are in equilibrium. So we have a forward and a reverse reaction occurring at the same rate. This is called the boiling point, where the liquid water is in dynamic equilibrium with gaseous water. So using the thermodynamic value, estimate the boiling point of water. Now, remember, at equilibrium, delta G is assigned as 0. And relationship that solves for the Kelvin temperature will have us take the delta H, which remember is always given to us in kilojoules per mole. Let's take the delta H, taking the sum of the product, which is the gaseous water value of negative 241.82 kilojoules per mole. And I'm going to subtract the reactant value, which is negative 286.83 kilojoules per mole. What is the heat of this reaction is taking the thermodynamic property of enthalpy, that's heat, and that is given to us as negative 241.82 minus a negative 286.83. This is 45.01 kilojoules. You know what? This is an endothermic value. It takes heat energy to make liquid water evaporate. That makes sense. Now, let's do the same for delta S of the reaction. And I did that work up here. I went into the thermodynamic properties chart and pulled up their delta S for us. The delta S for gaseous water is 188.8 joules per Kelvin mole, minus the value of entropy for liquid water was 70.1 joules per Kelvin mole. I'm going to subtract like units, and we find 188.8 minus 70.1. Delta S comes out with a value of 118.7 joules per Kelvin mole, or 0.1187 kilojoules per Kelvin mole. The temperature, which is what we're solving for, what is the boiling point approximately of water? We saw this formula. Do you remember? Enthalpy over entropy. So delta H is the bigger factor. 45.01 kilojoules per mole set over 0.1187 kilojoules per Kelvin mole. And notice here, kJs will cancel one another, and Kelvin will end up to be our solved unit. So 45.01 divided by 0.1187. This comes out to be 379.19 Kelvin units. And actually we can subtract out 273.15 to go back from Kelvin into Celsius. And our answer is 106.04 Celsius units, degrees Celsius, as the boiling point of water. Remember, boiling points are pressure dependent. So high altitudes have different boiling points based on pressure of the atmosphere, as in low pressure points. So that's approximately what our we always say water boils at 100, but that assumes standard pressure. So that number is in the ballpark. Okay, now free energy and equilibrium. Let's continue talking about equilibrium, knowing that that means a reverse and a forward reaction are occurring at the same rate. Free energy, we know, is viewed as that driving force. If the delta G is greater than 0, the delta G is greater than 0, that's a positive. Delta G, these are backwards. Delta G needs to be negative. Delta G needs to be positive. So if delta G is negative, we know that it's spontaneous in the forward direction. Delta G is positive. We know that the driving force is pushing us in the reverse direction. And if it's at 0, they're occurring at the same rate. We can show free energy and equilibrium related to one another in a non-standard condition with the following equation. If we're asked to solve for delta G at non-standard states, remember what standard states were? Standard states, we said, was 1 atmosphere pressure, 298 Kelvin, 1 molar solutions. If we had aqueous solutions, those are standard states. What if we're not using standard states? How can we solve for delta G at a non-standard condition? Well, we do so by adding a little corrective factor onto the standard conditions. So this is the standard conditions where we took products minus reactants. And we add RT ln Q. What does that mean? Let's dive into each one of those variables. Now, R comes to us from the ideal gas law. Do you remember from first term, PV equals nRT? R is the ideal gas law constant. And in the metric system, where we used kilopascals or kilojoules per Kelvin mole, 8.31 was a joule per Kelvin mole for the ideal gas constant. Now remember, we often use kilojoules for Gibbs free energy. So 0.00831 kilojoules per Kelvin mole is the ideal gas constant in our equation RT ln Q. R is the ideal gas law constant. T, of course, is the Kelvin temperature. And Q stands for a reaction quotient. And this will be a brand new term to the vast majority of us because we've not yet done our equilibrium chapter. So my next few slides, I'm going to just really emphasize what Q is in terms of its definition, a reaction quotient. I have to be comfortable with writing out reaction quotients in order to calculate Gibbs free energy at non-standard conditions. So let's take a first step in understanding, and I know this will come up again in our next chapter, equilibrium. I'm seeding a lot of that chapter in this particular section. Reaction quotients, which is Q in that last slide. Again, ultimately our goal is to find delta G for non-standard conditions, and it relies on a reaction quotient. It's derived directly from the stoichiometry of the balanced equation. These little letters here represent coefficients, M, N, X, and Y, and they're placed before the reactants and the products. Notice that we take a quotient of the ratio of products over reactants, in which the coefficients become the power with which we raise each ingredient. So the reaction quotient, products over reactants, the product C raised to the power of X, where X is its coefficient, times the product D raised to the power of its coefficient Y, set over the reactants. The first reactant is A raised to the order of M. The M is the coefficient. It becomes the factor to which we raise the A. And B raised to the power of N. We can talk about coefficients in stoichiometry in terms of writing out reaction quotients. If the ingredients are given to us in molarity units, we write QC, which stands for concentration in molarity. Another type of reaction quotient relates to pressure. So if these are aqueous solutions, the concentration is molarity units, and those become the values inside the brackets. The brackets stand for molarity units. And I'm sure you remember this from your solution stoichiometry, your solution, when you learned how to make dilutions and so forth. This is standing for molarity units, the brackets. The other type of reaction quotient is P, where P stands for pressure of gaseous reactants and moles, and those are going to be measured in atmospheres of pressure. So the partial pressure of A raised to some power of M, for instance. Partial pressures are how we measure gaseous reactants and products. Let's practice writing out reaction quotients. This is no math, we're just writing out. And it says, write the concentration-based reaction quotient. Concentration-based uses brackets to represent molarity. So for example, letter A, my reaction quotient in a concentration unit of molarity has me take the product ozone, O3, raised to the power of 2, set over molecular oxygen, the reactant, raised to the power of 3, its coefficient. Products over reactants, where the coefficients become the powers with which you raise. How about B? The product is ammonia, NH3. In a bracket to represent molarity units, ammonia raised to the power of 2 for its coefficient. Set over molecular nitrogen, it has a power of 1, you may leave it off, times reaction quotients, we multiply these together, times molecular hydrogen's concentration cubed. That's the reaction quotient written in a concentration unit. Now let's say if it wanted us to, it didn't, but if I wanted to write out the partial pressure of this particular, and it would work fine because these are all gases, I would simply rewrite this by saying the partial pressure in an atmosphere instead of molarity of ammonia squared set over the partial pressure of nitrogen times the partial pressure of hydrogen, and that would be cubed. For KPs, gases are the only reactants and products that exert pressure. So gaseous reactants and products only. And these concentration, you're looking at including just gases or aqueous solutions. They can have a molarity unit. So drop out any pure solid, any pure liquid from your equilibrium expression. We had one more, and that was letter C. Back to a QC, a reaction quotient of products over reactants. The molarity of nitrogen dioxide raised to the 4th power times the molarity of gaseous water raised to the 6th power set over ammonia. The molarity of ammonia would be raised to the 4th power times gaseous oxygen's molarity raised to the 7th power. Products over reactants, coefficients become the powers with which you raise the molarity units to. Now reminding us, why am I doing that? That's Q in this formula. I want to calculate delta G for non-standard conditions. It relates to concentrations or pressure units with which you're running the reaction at. That's why I had to digress and make sure we understand what's being asked of us in terms of reaction quotients. Let's apply that equation now, where it says, let's calculate delta G under non-standard conditions. Do you have that equation handy? Delta G for non-standard conditions can be found by taking the delta G of the standard state and adding a corrective R, ideal gas constant, T, the Kelvin temperature, times the natural log of the reaction quotient. Remember, Ln on your calculator is natural log. It's based on Euler's number. The opposite of natural log is that little e sign you see on your calculator. E to the x is kind of the opposite of natural log. It's very different than a log base 10, where 10 to the x is the opposite there. So log is a base 10. A natural log has a base of Euler's number. So again, that math, I just want to make sure you see the difference. We're not taking base 10 logs. We're taking natural logs. So make sure you're hitting the ln key on your calculator, not log, natural log. What is the free energy change for the process here under the specified conditions? Here's my equation. Molecular ammonia decomposes into its elements, hydrogen and nitrogen. And the delta G for that reaction standard state is 33 kilojoules per mole. You can see this is non-spontaneous in the forward direction because it's a positive delta G. The reaction quotient is going to be given to us in partial pressure. Notice these are now atmospheres. Those are atmospheres. The product, the partial pressure of hydrogen cubed times the partial pressure of nitrogen raised to the first power, its coefficient, set over the partial pressure of ammonia, and that needs to be squared from its coefficient. Well, let's plug those in. The partial pressure of hydrogen, 0.25 atmospheres. And that needs to be cubed because the coefficient in front of hydrogen is a 3, times the partial pressure of nitrogen, which is 0.87, all over the partial pressure of ammonia, 12.9 atmospheres. That's very high pressure. And that needs to be squared based on its coefficient. So let's solve for Q so we can plug it into our formula above. 0.25 cubed times 0.87 divided by 12.9 squared. And Q comes out to be a very small number, 8.17, I'll round there, times 10 to the negative 5. There's no units on reaction to quotient. It's just a number. And that number gives us insight into whether the reaction is favorable forward direction or favorable in a reverse direction. All right, we have Q. We're being asked to solve for delta G at the non-standard state. So delta G is equal to, this is the non-standard state value, is equal to the delta G of the standard state, which was given to us, 33.0, and that's in a kilojoule per mole. So that's delta G of standard state. I'm going to write SS, delta G standard state, and you know that's standard because it has that little subnaught there after it. Plus RT. Now R in a kilojoule, 0.00831 kilojoule per Kelvin mole. That's the ideal gas constant from our Puvnert equation, but in a kilojoule value. The temperature with which we ran, 25 degrees Celsius, and so that's 298 Kelvin. Times the natural log of Q, 8.17 times 10 to the negative 5th. I'm going to simplify RT ln Q and write that value down. That came out to be negative 23.309. I'll just round a little bit, and that's a kJ per mole. Over here, I'm going to add now the 33, the standard state kJ per mole, pulling out delta G of the non-standard conditions. So while that's on my screen, I'm going to add 33. And I get 9.69 kJs per mole. A non-spontaneous reaction as written. All right. We just solved for the Gibbs free energy of a reaction being run at non-standard conditions. Step 1, we had to find the reaction quotient. That quotient is given to me in terms of the conditions the reaction is being run at, different pressures. Remember, standard conditions, standard states, pressure is always 1 atmosphere. So every one of these would have had to been a 1 ATM to have a standard state condition calculated. Well, clearly they are not all 1 atmospheres. So that requires me to add on RT ln Q to the standard state value to solve for the new delta G. Use this equation anytime you're being asked to solve for non-standard conditions. Let's do a read through on another practice problem, and I'm going to ask you to work through it once we read it. All right, so we have a gaseous reaction. Standard conditions are 298 and 1 atmosphere for pressure. Those are standard state conditions. And when that happens, the standard state delta G is given as negative 69 kilojoules per mole. For the process of 2 moles of NO reacting with oxygen, forming 2 gaseous moles of NO2. That reaction is spontaneous in the forward direction. Now, what is the delta G for the reaction? Same temperature, 298 Kelvin, but now instead of all having 1 atmospheres, we have different values for pressure. Alrighty. So we have to begin by figuring out Q, the reaction quotient. And Q is going to be measured in partial pressures of products over reactants. The product of nitrogen dioxide's partial pressure squared from its coefficient, set over the partial pressure of the first reactant, NO, squared from its coefficient, times the partial pressure of molecular oxygen, and it's just going to be to the first power since its coefficient is a 1. Products over reactants, in which the coefficients become the powers with which you raise. We're solving for Q, which stands for the reaction quotient. Well, on the top, partial pressure of nitrogen dioxide, 0.7 squared, set over partial pressure of NO, which is 0.2 squared, and the partial pressure of oxygen, which is 0.3 raised to the first power. Let's solve for Q, the reaction quotient, in partial pressure units of atmospheres. 0.7 squared divided by 0.2 squared and 0.3. 40.83, no units on the reaction quotient. It's just a ratio of products over reactants. But now I can use that to solve for the non-standard states. Remember my equation? I need the standard state value, delta G, which is standard, minus, whoops, that's not minus, it's plus, right? For the standard state conditions, plus RT ln Q. Yeah. Let me get my work back up here. There we go. Okay, so we want delta G, which was negative 69, plus R 00831 kilojoules per Kelvin mole. That's your ideal gas constant from your gas laws chapter. 298 Kelvin units, standard temperature, times the natural log, ln(q), natural log of 40.83. I like to simplify RT ln Q first. I just want to get that done. 0.00831 times 298 times the natural log of 40.83. That simplifies to 9.1859. We'll figure out sig figs here at the end. And so I'm going to add that to a negative 69. And delta G of our reaction in non-standard conditions comes out negative 59.81. I'll leave it as 1 decimal since that's what this value had, 1 decimal. And that ends up to be in a kilojoule per mole. Pause the video if you need to really think through the process solving delta G in non-standard conditions. Reaction to quotients. We're going to talk a lot more about that in our next chapter on equilibrium as well. You want to try one? I would encourage you to work through this one on your own and then pause, come back to me when you're ready to check. Give yourself the think time to process. Try solving this problem and then come back to me. All right, let's see what we have. The reaction to quotient this time is going to be in concentration units, isn't it? Because I'm given moles of gas per liter of solution. Remember that molarity is defined as the number of moles of solute per liter of solution. And therefore, since we had 0.1 mole of the gas in a 5-liter mixture, the molarity of your solution, you had to find that, didn't you? You had to say 0.1 divided by 5. And that, of course, is 0.02 molar. And that's for each one of your reactants and products. The free energy change for this reaction is the same. So the reaction quotient is going to be the concentration of hydrogen cubed times the molar concentration of nitrogen to the first power set over the molar concentration of ammonia squared. Products over reactants, where the coefficients become the power with which you raise. Now each one of these was the same value, 0.02. So you have 0.02 cubed times 0.02 to the first over 0.02 squared. What does that simplify to? I mean, you could literally hit it out, or you realize you could simplify as well. 0.02 to the fourth over 0.02 squared leaves you with 0.02 squared overall, doesn't it? That's your reaction quotient. Okay. Delta G for non-standard states can be found by taking the standard state delta G and adding on a correction RT ln Q. Delta G in the natural state or standard state was given to us as 33 kilojoules per mole plus R is the ideal gas constant, but written in a kilojoule per Kelvin mole, so 0.00831, times the Kelvin temperature, (8, 14, 10, 11). So that's 1148 Kelvin. Did you find that right here? 875 added to 273 gives us 1148 Kelvin units. And then we want to multiply that by the natural log of the Q that we found, which was 4 times 10 to the negative 4. Now I just like to simplify RT ln Q first, just so that the math becomes a little easier to manage. So I have 33.0 kilojoules per mole plus, let me hit RT ln Q, 0.00831 times 1148 times the natural log of 0.0004. And that comes out to be negative 74.64 kilojoules per mole. Add that to 33. And overall, we have a negative 41.64 kilojoules per mole for this reaction. And now you can see with these particular conditions, the reaction is now spontaneous in the forward direction. At a very, very high temperature, the reaction became spontaneous. How did you do? Did you work that one through correctly? I bet you did. I'm proud of you. I'm going to just keep working problems in the next few slides. The more examples I can leave you with, the better off you are on your homework and your upcoming test. And I've just captured some old test questions, and I just want to talk out loud and kind of share them with you. We can calculate the delta G of a reaction at 298 under the following conditions shown below for the following equation. So again, we're asked to solve for non-standard state. Our formula, the delta G for a reaction non-standard other than 1 atmosphere for gases, 1 molar for concentration, and 298 Kelvin units are all standard states. We take the delta G of the reaction in standard conditions and we add on a corrective, RT ln Q. So Q is given in pressure, and you remember that we only include gaseous reactants and products for pressure. So it makes no sense to say, what pressure does solid calcium carbonate exert? It doesn't exert a pressure. It's in a solid phase. What does the pressure for calcium oxide? Does that make any sense? Let me rewrite this. Calcium carbonate as a solid decomposes into calcium oxide solid plus carbon dioxide gas. And this delta G standard conditions is the 131.1 kilojoules of energy. That's the equation kind of written out in a better form. And the only gaseous reactant or product is carbon dioxide. So Q is very simple here. Will be in a partial pressure, and it's equal to the partial pressure of carbon dioxide raised to the first power. That's the only ingredient involved in the quotient expression. So this becomes R 0.00831 times 298 Kelvin times the natural log of 0.033 atmospheres. That's our reaction quotient. The value right here. The standard state value was 131.1 kilojoules. Let's solve for delta G in the non-standard conditions. So the reason I picked this as an example was to remind you that only pure gases drop out liquids, drop out solids, as they do not exert pressures. We're only including partial pressure of carbon dioxide. 0.00831 times 298 times the natural log of 0.033 came out to negative 8.4475. I'll just consider sig figs here in a moment. So while that's on my screen, I'll go plus 131. And delta G in the non-standard condition came out to be 122.6 kilojoules of energy. Still a non-spontaneous in the forward direction. Ready to keep going? I'd like to keep working practice problems. If you're sticking with me, great. Certainly work ahead and just forward if you want to find our simple solutions together. But I like to share as many practices as you'll stick with me for. Here's another old test question. Calculate the delta G of the reaction shown below. I'm going to rewrite the equation because it kind of gets choppy here. I have two gaseous mercuries, 2Hg gas, plus molecular oxygen as a gas, forming two mercury oxide solids. And this delta G in a standard condition is given as negative 180.8 kilojoules. So that is spontaneous in the forward direction with its negative sign. Calculate for non-standard conditions. All right, so we need a Q with reaction quotient. And remember that pure solids, pure liquids drop out. So this expression is going to be given to us as really there's no gaseous product. So there's nothing. I'm going to just put a 1 there so we can see that the mercury Hg, which is 0.025, will need to be squared from its coefficient times molecular oxygen, which is 0.037, and it's just to the first power since its coefficient is a 1. Since those are both reactants, they belong under this fraction, right? The quotient will have the reactants at the bottom. So 1 divided by 0.025 squared and by 0.037 gives me a reaction quotient of a very large number, 43243.2. Very large. That tells us that the forward direction is very much favored, as does the negative delta G sign. The delta G of this reaction in the non-standard conditions is found by taking the delta G standard, negative 180.8 kilojoules, and adding on a conversion factor, a little adjusting factor, RT ln Q. R is the ideal gas constant in a kilojoule, 0.8, that's a weird 8, 0.831, there we go, 00831 kJs per Kelvin mole, times your standard temperature, 298 Kelvin, times the natural log of this very large reaction quotient, 43243.2. Let's simplify RT ln Q. And this comes out to be positive 26.43, negative 180.8. So while that's on your screen, I'm going to add the negative 180.8. And the delta G for this reaction in non-standard conditions, still negative 154 point, and I'm going to round that to 4 kilojoules. Still a spontaneous reaction due to the negative delta G. How are you doing? Are they getting easier with each practice? I sure hope so. So this free energy and equilibrium, reminding us of what we're really doing here. If we're in non-standard states, we know that the delta G is related to standard plus RT ln Q. But what if we are at standard states and the reaction is indeed at equilibrium? The reaction quotient is equal to K, and we're going to spend a whole lot of time talking about equilibrium constants in our very next chapter. And here I'm just going to be able to seed this so when you see it next chapter, it will sound familiar. K, or sometimes KEQ, we just talked about a KP and KC. for reaction to quotients is known as the equilibrium constant. And that's simply the ratio of products over reactants where the coefficients become powers with which we raise. So instead of having Q in a non-standard state, at equilibrium, we're going to call that K, the equilibrium constant. But notice the formula really is the same, isn't it? For a system at equilibrium, Q is the same as K. The reaction to quotient is equal to the equilibrium constant. And we know that the value of 0 is given to that Gibbs free energy. So the standard state Gibbs free energy can be set equal to negative RT ln K. And remember, the opposite of natural log is Euler's number. So to rearrange that equation, the equilibrium constant is equal to Euler's number. On your calculator, just remind yourself, it's the opposite of natural log. So sometimes you have to hit second function ln to find Euler's number. E raised to the x sits on top of the natural log key. Negative delta G over RT, that's rearranging those. So again, these are on your equation page. Know these for the test. The equilibrium constant gives us an idea of the direction the arrow is favored, right? Is it the forward direction or the reverse direction? When we have a spontaneous reaction, we know delta G is negative. That means that we have more products than reactants, that the forward reaction is being favored in terms of quantity. There's more product than reactant. Now, it doesn't say about the rate. The rates are the same, but it doesn't mean they have to be the same amounts. So more products than reactants when K is greater than 1. If K is less than 1, delta G is 0. That's non-spontaneous in the forward direction. That means that the reverse direction is being favored for quantity. That we have more reactants than products. And if delta G is 0, K will be exactly 1 since we have an equal amount of products and reactants. So delta G is negative RT ln K at standard conditions. Let's model a problem from your homework. What is the value of K? Now I want you to know K is what we call the equilibrium expression. Well, I'm going to call that the equilibrium constant. It is found the exact same way as writing Q. So if we had a reaction A plus B goes on to make C and D, the equilibrium constant would be the products raised to their coefficients over the reactants raised to their coefficients. This is exactly the same. It's just that now we're at standard state. Whereas Q would be non-standard states. That's the only difference, that we have those two different letters. Alrighty. So what we know from our formula, delta G at a standard state condition is found by taking negative RT natural log K. Alrighty. What is the value of the equilibrium constant for this reaction? At 298 Kelvin. So notice we're at a standard condition, so that's 12.56 kilojoule per mole equal negative RT ln K. So negative 0.00831 kilojoules per Kelvin mole times 298 Kelvin times natural log of K. Remember how we manipulated that a moment ago on that previous slide? If we want to isolate K, it's the same equation. We're just taking the opposite of the natural log. So let's rewrite that as well. That if we'd want to know K, just take the opposite sign. And I should probably write that on the equation page before I print that off. E raised to the negative, remember what that was? Right here, negative delta G over RT. And I'm going to write this again over and over so that you get familiar with what that E represents. It's the natural log base, Euler's number. I'd like to know K, the equilibrium constant. So I'm going to take that value negative and the negative sign here. Delta G was positive, so it's negative of a positive 12.56 over 0.00831 times 298. And that's all going to be raised from Euler's number, E raised to that power. I'm going to simplify this bracket. So in my calculator now, I'm going to go 12.56 divided by parenthesis 0.00831 times 298. And my screen reads 5.0719. Alrighty. Now, my key sequence to solve for K, I'm going to hit second function of the natural log of negative 5.0719. Second function ln is the way that you take the opposite of natural log, and that's going to be E raised to the negative 5.0719. Alrighty, so I'm going to hit second function natural log. I get an E with a little caret key on my screen, negative 5.0719, close parenthesis, and the equilibrium constant came out to be 0.00627. No units on an equilibrium constant or a reaction to quotient. It's just a number, and it's the size of the number, the magnitude of the number that's interesting to the chemist. This is a number that's very small, being favored in the reaction. There, more reactants than products. Just to emphasize what that might look like in terms of this reaction, we didn't really have but just a generic reaction. It says A and B go on to make C and D. But I'm telling you that in terms of amounts, there's a whole lot more A and B as compared to C and D in the vessel. That the small K value favors the reactants. Good work. We're doing good work. I'm so proud of you. This is an example, probably one of the last ones here, and I have one more at the end. So we have two more examples. I wanted to peek ahead, and just stay with me and work. More practice, the better. Again, pause the video and work ahead. That's so much more interesting, and then come back for feedback. Consider the decomposition of a metallic oxide into its elements. And I'm given the delta G of formation. Notice that the elements in their natural state are assigned a 0. So standard state Gibbs free energy allows us to find the delta G of a reaction by taking the sum of the delta G, delta G of products minus the reactants. And so here, since both of these are elemental forms, they have assigned 0 and then minus the negative 7.10. This comes out to be a positive 7.10 kilojoules per mole. So this is non-spontaneous in the forward direction. How about the equilibrium constant? Well, K is equal to Euler's number E raised to the negative of delta G over RT. We just practiced one of those. So the base of the natural log, right, E raised to the negative 7.10 over 0.00831 times 298. I'm going to hit that with you. 7.1 divided by 0.00831 and 298 gives me a number of 6.253. And that's enough there. So I'm going to then say the opposite of natural log is Euler's number. So second function ln of that answer. And K comes out to be 519.8. No units on the K. Now that's a really large number. So that's telling me, I'm going to see if I did that right. I'm going to check my math again. 7.1 divided by 0.00831 divided by 298. I got that wrong. Thank you for helping me find that. 2.87 is what my screen says. And then second function natural log raised to the negative of that answer. Yeah, that's a number that makes way more sense. 0.569. Here's how I knew I made a mistake. That I knew that K had to be a small number, meaning that the reverse reaction was being favored, because the positive delta G tells me that the forward reaction is non-spontaneous. So therefore, K is not going to favor the forward direction. It's going to favor the reverse direction, meaning that I need a very small K value. So that's how I knew I made a mistake and backed up and checked my work. No worries, I caught it. All right, and now the last part here, what is the equilibrium pressure of oxygen? Well, remember the K expression simply says it will be the partial pressure of oxygen in the gaseous form, and that's going to be raised to its coefficient of 1/2. And you know what else is kind of fun? Pure solids, pure liquids just drop out of the equilibrium expression, and therefore there's only one ingredient equal to the K, the equilibrium. And this is what we're trying to solve for, the partial pressure of oxygen. K we just solved for is 0.0569 is now equal to what my target is, the partial pressure of oxygen raised to 1/2. So I want to isolate the partial pressure of oxygen to both sides. We'll simply square to get rid of the 1/2 power. Opposite of square root is squaring. 1/2 power is a square root. So I'm going to square both sides. So I'm going to square that answer, and I get 0.0032 atmospheres of pressure as the partial pressure of oxygen. One more just like it. I snipped it off of an old test question. Calculate the equilibrium constant. The equilibrium constant is found by using the opposite of the natural log raised to the delta G standard over RT. This time we have to work for delta G. Delta G is given to us, but only indirectly. Delta G can be found by taking negative 94.9 kilojoules, that's our enthalpy value, delta H, minus T 549 Kelvin units times, well, I'm going to slide this decimal over, negative 0.2242 kilojoules per Kelvin. Kelvin's canceled, and I'm subtracting like units. So let's hit for delta G. Negative, well, I'm going to solve that bracket first. 549 times negative 0.2242. And that simplifies to negative 123.0858. Did you find that on your screen? And then I'm going to say negative 94.9 minus that answer, and we get a positive 28.1859. Let me just round that. 28 point, we better have one decimal place, so I'm going to say 0.2. Okay, so there we found delta G finally. So I have Euler's number, which is the opposite of a natural log, raised to the negative 28.2 kilojoules over R times T and there's our answer waiting to be simplified. So divided by 0.00831 divided by 549. Natural log. So the opposite of ln is Euler's number. E raised to the negative. Previous answer on my calculator. And K comes out to be 0.0021, I'll round, and no units on an equilibrium constant. Did you find that as well? That's the end of our video lessons. My advice, practice, practice, practice. There's a lot of formulas to keep straight in your head on this particular chapter. So you're ready to kind of compile all your notes, submit them into the Dropbox, and I look forward to seeing all your hard work very soon.